Happy Monday, everybody. Week 9, dangerously close to the end of the quarter. Today we are going to just close up some final conversations we were having about quicksort, and then I am going to introduce you to this algorithmic optimization approach called dynamic programming that just keeps on showing up more and more in interviews and also is just so delightfully clever that I think it's super useful to think about. I also said that the midterm was going to be graded, and I will tell you that I am now looking at my back end of it, and there's probably only 2 things left to grade. It's so dangerously close that I suspect we'll be able to hit release on this, and actually now I do feel like there's enough data for me to say that it's looking like the overall median on the final is coming out to about an 80%, which is great. I always try to shoot for a high 70s, low 80s general sort of median. I use medians, not averages, on my exam. So things are looking pretty okay, knock on wood. But we will... Based on the state of these grades, I think we're going to be able to release these. Yeah, I literally, oh my gosh, even while we were chatting, whatever magical TA is out there, I see you having finished great things as I was just speaking. So I'm assuming all I need to do now is go back through and just sanity check these things, and I'll release them a little later this afternoon. So thank you so much for your patience on that. We are also finalizing the final exam logistics tomorrow. So on Wednesday in lecture, I'll have a lot more details about what the final exam is going to look like, and maybe I'll take this sort of data so we can talk through how the midterm shook out, and I'll share that in Wednesday's lecture. The checkpoint for the P4 has passed, so if you have not started P4, code red, okay? Please start it. And then, of course, exercise 6 is due this Friday. Does anybody have any other administrative questions before we dive into our content for the day? No? Cool. All right. Okay. I did make a poll everywhere live. Again, poll everywheres are not graded on correctness at all, and so far we've only chatted about one possible way to pick a pivot for quicksort, but as it turns out, there's lots of ways to pick pivots for quicksort, so I want to take another few minutes and just chat through what these things are. I think it gives another good example of algorithm design, so we're going to chat through that for the very beginning. So, reminder that we are in the algorithm design subcategory of what we would call divide and conquer. And the principle of divide and conquer is that any given solution is the summation of a bunch of sub problems, right? One big problem is really just a bunch of sub problems added up together. And that's really the foundation of recursion in general, right? We take in an input and then we reduce that input down to a base case. Once we hit the base case, then we sort of roll our work back up, right? So merge sort decided to do divide and then do all the work on the conquer, right? We looked at a set and we were like, hey, if there is more than one thing to sort, that's just too complicated for me. And I'm just going to split my set until I get down to a set of 1. And it's really easy to sort an item of 1 because it's just already sorted. And then I interweave sorted lists back together. Quicksort is kind of the opposite of merge sort in terms of where the work is happening, in that we've picked this pivot, and the pivot is giving us this sort of intentional way to decide how we're dividing that work. And so as you can imagine, picking a great pivot, we sort of chatted about this at the end of lecture on Friday. If we pick a really bad pivot, and I think we sort of chatted about this, i.e., for example, the smallest value in the set kind of pivot, we're not really dividing the work at all, right? And so picking a great pivot lets us do much more intelligent dividing. And then in quicksort, our conquer is just they're already sorted. They're already in the right order to mush them back together. So merge sort and quicksort are interesting sort of mirror images of each other in that way. Does anybody have any questions about that before I dive deeper into talking through this idea of how we pick the pivot. I know I'm just sort of reminding you of things we chatted about on Friday. Cool. Okay, so this is how we started, right? Where, well, we just need to pick a pivot. And remember, the way that this functions is that we pick a pivot, and then as we move through the rest of the collection, so here we've picked the pivot that's at index 0, and then what we did is we asked ourselves, does 2 belong on the left or the right of the pivot? Went to the left. Does 91 belong on the left or the right? The right. 22, left or right? And see how everything stays in the same relative order? We're just dividing it around this pivot. So like, for example, we don't reorder this 1 in front of the 2. It came after the 2 originally. And we just sort of break down and break down and break down. And then eventually, once we get down to these single values, we kind of order them back together, so on and so forth. And then I think we watched our delightful algorithmics dance it out. Okay. Yep. Okay, great. So, and reminder that the way that we pick the pivot is we don't just pick the pivot at the very beginning. The 8 is only the pivot for the first divide. We need to pick a new pivot at every single level because the pivot is what enables us to continually divide at each sort of level down to get to the one lists of one kind of situation. So in this case, that was a really efficient choice. Just pulling whatever is at index 0 is a really cheap and easy choice. There's going to be an index 0 of every single list at every level. So that's kind of why that's a pretty traditional one. There's the combined steps. I think we talked through these pieces. And I think we chatted a little bit. I think this might be where we sort of left off. And so the key here with quicksort, that's a little funny, is that if we pivot and we don't really split things in half, we're not really reducing the size of the input to the recursive calls. And so that's where this n-1 comes from in the runtime, where I've taken n inputs into one list and then maybe just shaved the pivot itself off of that. That's kind of like the worst possible scenario. And that actually ends up being this n-squared worst case runtime. So it is one thing to know about quicksort is that it does asymptotically have a worst case runtime possibility of n squared. But if we pick a really great pivot and we split things in half every time, we get that magical log n kind of devising, and we get to that n log n, which is technically the best you can do for any comparison sort. And so in practice, yeah, there's a lot of amortized analysis, but we consider quicksort in practice to be an n log n runtime. So if you're in an interview and people are like, what's the runtime of quicksort? They are expecting you to probably say n log n. However, you do want to keep in the back of your head that it has a worst case possibility of n squared. Just so you're aware, no, it's not stable. It's not stable because we're pivoting and moving things around in that kind of funky way. And in place actually can be done. I think the algorithmics danced an in-place version of this where they were sort of like swapping the pivot around in interesting places. So that is also another benefit of quicksort on top of, say, merge sort, that we can do this in place, which is really nice and reduces our memory usage. But okay, can we do better? How can we avoid hitting that worst case? Here are a few different options for finding a pivot. So we talked about just taking the first element. We could try to get the optimal pivot, where the optimal pivot is the value that perfectly cuts the data in half, which would be the median value. So that's one way. We could just be like, hey, we know what the optimal is going to be. Let's just go find that value. But maybe that's going to have a lot of math involved. Maybe that would mean we'd have to loop over everything and we'd incur an extra linear runtime just in the act of trying to find the pivot, which is probably not what we're looking for. So maybe instead we can kind of do this compromise where instead of taking the median of the full array, which would require us to loop over n items and then calculate their median, what if I just spontaneously looked at the thing at index 0, the thing at the very last index, or the thing in the middle, and then I took the median of those 3 values? And the supposition there is that a median of 3 values is probably better than just taking the thing at index 0, but 3 values is still constant time in relation to n. And if we maybe take the thing at the front, the thing at the back, and the thing at the middle, and you have some type of data set that may or may not be in some relatively sorted order, at the very least, hopefully we're getting numbers that are different from one another, but that's not a guarantee. So that's one strategy. Or, when in doubt, pick a random element. Maybe, like that's essentially what we were doing by picking the thing at index 0. We were just picking a random value, but we're like, hey, let's just pick whatever's at index 0. But maybe we recognize that like that might always kind of be a small value depending on your data set, especially if it's sequential. So maybe we just every time generate a random index of the array and grab something out, and that gives us a little bit higher of an opportunity to pick a more median value to the overall set. Yeah. So we are going to be doing, like, this is all, you're right, this makes sense, like, and also makes sense in, like, when we're sorting int values, but when we're sorting string values, we're probably sorting by alphabetization. So in that case, we'd probably be picking the, like, word that starts with the letter that's closest to the middle of the alphabet, or, the word that essentially would come in the middle of the sorted order. So, and, whatever that equivalent is alphabetization. Any other questions? I think I've got more slides to dig into these in more detail. Yeah. Okay, so let's talk through some of these options. And honestly, these options remind me a lot of when we're trying to figure out the hash, when we were building a hash table. Remember, when we were doing hash tables, we knew we had that like constant time lookup, constant time put, as long as there were no collisions. But it took us a little bit of sort of like mathematics or, operations to get to a hash code that was less likely to collide. And so we had to sort of trade off, like how much computation do we want to do to reduce the collisions versus, what is going to impact our overall runtime. And I find this picking a pivot reminds me a lot of that, right? Like we're trying to pick a pivot intelligently, but we're not trying to spend so much computation that we lose that super quickness that comes with quicksort. So when we're thinking about picking the pivot, like if we were doing that first one that we sort of talked through, if we just take the first element, it's very fast. Like accessing at index 0, boom, constant time lookup, we go right into that index of the array. But it has that worst case, like we don't know, like especially if it's a sorted list, that's going to be a really bad situation, right? The median of the full array, like I said, we could actually find the median. You can Google something called quick select, which will help find the median in an n runtime. So this can then get you to a guaranteed n log n runtime. We are incurring a factor of n every time we sort of like run this thing, but that still keeps us in the same complexity class. However, this thing here, this constant factors are awful. When we say that is, we've been talking about the runtime for things when we can look at it asymptotically. And you know how I kept being like, don't ignore those numbers. Those numbers sort of fade away to infinity. We don't care about those numbers. Now I'm doing that really annoying thing where that thing I told you that didn't matter is now listed on a slide as somehow mattering. And a lot of times that's what we are talking about when it comes to quicksort, is that we are now getting into a category of sorting algorithms that all have n log n. And so those constant factors, the coefficients we waved away, the extra numbers on the back, things like that, those are going to start to impact these things. And so in this case, I can just promise you that this particular implementation of quicksort, those constant factors actually are so gross that even though the asymptotic runtime is theoretically n log n, in like actual clocked time it takes this version of quicksort to execute, it actually ends up running pretty slow. So instead of doing that whole, hey, let's go through and pick the median value every time, well, then we could do this, take the median of the first, last, and middle, makes the pivot slightly more content aware. At least we won't select the very smallest or the very largest item. we might end up with the second smallest or the second largest, right? So we could still end up with a worst case of n squared. But on real world data, this actually tends to perform very well. And so you will actually find that this is a pretty common implementation of quicksort pivot selection. Taking the first element, pretty common. Taking the median of the first, last, and middle, pretty common. And the picking of the random element, this is also like got all the same, like it could have that, you know, sort of n squared runtime. But in general, it doesn't really help us that much more over just taking the very first element. So you probably will find people either do this one, take the first element, or this one, take the median of the first, last, and the middle. Does anyone have any questions as to like the trade-offs of these things, or how they impact the algorithm? Yeah.
What's the computation time to find a random element?
The computation time to find a random element, it sort of depends on the language. Each language implements it. I mean, in this case, it would be constant and compared to n, but a lot of times the way it's done is they will take a timestamp from your computer, and then there is this magical random algorithm that's not random, but we seed it with a timestamp, and it is not the cheapest kind of thing, but it's certainly cheaper than, say, a linear runtime. It would be a constant. Yeah. Yes, question.
If finding the median of the first, last, and middle elements is about like a constant runtime, how come we don't like choose more than 3, like 5 or 10?
And I think that's a great question. Like, if this is constant, and this is constant because we're comparing specifically 3 values, and 3 values is constant and compared to n, right? And so to your question, why don't we pick 5 values? Why don't we pick 10 values? We could do that, right? The reason we're picking 3 in this case is because then we are like, there is an actual median of those 3. And remember, we're going to have to do this at every level of the tree. And so eventually we're going to have to pick pivots on a list that has 1 item in it, has 2 items in it, has 3 items in it kind of thing. And so if that was much larger, then that sort of like algorithm just would work less and less as we get deeper into the recursion call stack here. Yeah.
From what I understand of like a median method, so we essentially find a median, and then we kind of go through the array again and find the value closest to that median value that we're looking for.
Sorry, you mean for this one?
For take a median of the first, last, and middle, right?
Yeah.
Let's just say like we have elements, and like the first one is 1, the second one is 2, the third one is 3. So that would come up with the median value, or I guess that's a bad example, but let's just say the median value that we're looking for isn't in our array. Like, for example.
Oh, okay. Thank you. I think that's a good clarification. When I say the median of these 3, oh yeah, there we go. Thanks, pass Casey. When I say the median of these 3, it will be one of these 3 that we select. So we're selecting the specific value, not like computing what the average middle value would be.
So, yeah, okay, that makes sense.
Yeah. Okay, cool. Any other questions so far? Cool. If you feel compelled to update your poll everywhere response, you can, but I don't care at all what you put in there. I just want you to get your point. That's what you deserve. Okay, so here is an example of what I mean when I say we're picking the median of those first 3. So what we would do is we'd look at the thing at index 0, we'd look at the last index, and we look at the middle index, which is going to follow integer division. So we're going to end up at index 4 out of 9. And we say, hey, look, between an 8, a 0, and a 6, what's the median value? The 6 is the median value, so we've picked that as a pivot. So now what we're going to do is we're going to sort of swap that 6 into index 0. We just swapped it with the 8. And now we've got these sort of arrows, and I'm sorry it adjusted this color automatically on me. And we're just going to kind of like keep things and swap things around until what we end up with is now we have this portion is the pre-pivot portion. This portion is the post-pivot portion. And then here's our pivot. So now this is also an example of how we've started to do this in place. And so what we did is, as you can see here, as I was looping through, I kind of had these 2 pointers, and I looked and I said, hey, is 1 less than 6? Yeah. Is 4 less than 6? Yeah. Is 9 less than 6? No. So I swapped it over to sort of like the back half where the after pivot collection is. And then I would look back at 2 and I'd say, is 2 less than 6? Yeah. Is 0 less than 6? Is 3 less than 6? Is 5 less than 6? So on and so forth. And so that's my way of just sort of separating out the values to either side of the pivot. And this swap here, that's also why it breaks stability in that little moment. Yeah.
How did you initialize like the 7 and 8 to be how did you know that they would be?
So here I just started another pointer and I worked from the back. And so these things are kind of happening simultaneously. Maybe I have some pseudocode for this. And so I would say, hey, is 8, and if you can't read this because I can barely read it, it says X is greater than or equal to 6. And so we'd say, hey, is 8 greater than or equal to 6? Yeah. Is 7 greater than or equal to 6? Yeah. Is 2? No. And so we would kind of go until we hit the first item that doesn't belong. And we go here until we hit the first item that doesn't belong. And that's when we would know, swap the 9 and 2. And then we continue until we have 2 more items that we need to swap and go like that. Yeah.
And so when you say we do them simultaneously, like how does that?
So we've got a loop that's going to start here and going to move this arrow until we hit a value that breaks this test. And then we're going to leave our arrow here. Okay. And then we're going to go to the back and we're going to loop here. We're going to do that until we get to a point where it breaks this arrow, and then we're going to leave the arrow there. And that you can kind of imagine, sorry for the animations, imagine the arrows are pointing here at the 9 and the 2. That's a swap moment. And then our arrows go again from where they sort of were left off in that place. We would let the blue arrow be like, okay, well now it's a 2, that's fine. Then it's a 0, that's fine. Then it's a 3, that's fine. 5, that's okay. And then we'd hit the 9, we'd be like, oh, stop there. And then we go from the back and we'd say 9, that's fine. Oh, and then our arrows would meet. And at the moments the arrows meet, we're like, sweet, we've pivoted everything appropriately. Yep, cool. Wow, and apparently this just doesn't have anything. Okay, yeah. So we just talked through that. So here's just a sorting summary. One thing I just wanted to sort of call out is that, no single sorting algorithm is technically the best. That might be a sort of sacrilegious thing to say to computer scientists. Some people will fight to the death for merge sort or fight to the death for quick sort. But here's what I'll tell you in general is that quick sort is called quick sort because in actuality, notice how it's just working within a singular array and it's doing those swaps and those comparisons. You're benefiting from caching and memory optimization and all that good stuff that I've sort of mentioned that engineers love about arrays. And so though quicksort has the same in practice runtime as merge sort, because it doesn't have that sort of make a new array, copy everything over and all that stuff, the constant factors of quicksort make quicksort truthfully named kind of the quickest sort. So if you were to just run this on a bunch of different examples of input, quicksort tends to run the actual quickest, especially on primitives. And so to our sort of question earlier about what about strings? That's a little harder to figure out. Yeah, it will literally take a little more computational error to figure energy to figure out what the median is, a more complicated object. So you'll find that the way Java has decided to implement its sorts, and so this is if you were to call capital A arrays.sort and pass in an array, it'll take in your array and whatever values are in it, and then it'll return back a new array with everything all nice and sorted. What it's doing under the hood is if you pass it in, it's going to use merge sort if you pass in an array of objects. And so maybe you pass an array of strings, maybe you pass in an array of student objects that their compare to method goes first by last name and then second by first name, et cetera, et cetera. However, if you have primitives, it uses something called dual pivot quicksort, which I didn't even fully go through, but you can imagine has 2 pivots and just sort of divides more quickly kind of thing. But in general, we find that the quicksort comparisons and those overall coefficients, they do overall add up to be quicker when you're running sorting on primitives like integer values. And then, hilariously, researchers have just tried sorts on so many things. Like I told you, computer scientists are obsessed with sorting. There's a bunch of brilliant researchers out there that just ran a bunch of different data through a bunch of the different sorts and have found out that if you have a, quote, reasonably short array of primitives, the actual fastest sort is insertion sort. And so if you call arrays.sort on an array of 48 or fewer primitive items, it's actually going to run insertion sort. And if you're like, Casey, how do we know that? Research, magic. I'm going to be real. I don't really know why, but they ran it in a bunch of real world scenarios. And so that's how Java breaks it down. It actually uses a combination of merge sort for objects, quick sort for large sets of primitives, and insertion sort for small sets of primitives. Any questions on sorting in general? This is the end of our conversation about sorts, at least. Yeah.
When you're sorting like objects and stuff, like what is it like sorting by? Is it by like hash code or like what is the order that it puts stuff in?
It's reliant on the compare to method. So the compare to method has to be implemented, and your compare to method, right, like takes in a other object of yourself and returns 0 if you're equal, -1 if you're less than, or 1 if you're greater than. And so it relies on however the object is defined that you're being compared. So like if your object has maybe like an ID value or something, maybe it just sorts based on that. Or maybe if your object has a last name, it sorts based on that, would be based on how the object is defined, their compare to method. Yeah. Any other questions? Yeah. So in this case, this is just, they ran through a bunch of research. And I think in general for this situation, if you think about like the overall like speed at which like it's not doing those recursive calls all the way down to the base case, it's not picking those pivots and things like that. And so when you have a small collection of things, insertion sort probably is just so direct and immediate that it ends up when you just like straight up like start a, like if you think of starting a stopwatch and running all of the sorts on say like 48 items, insertion sort, just research has found, comes out fastest. So I don't know why in theory, other than like they did a bunch of trials. Yeah. Any other questions? I think this is my, yeah, okay, cool. So yeah, you can read all these things. So really, can we do better than n log n for comparison sorts? No, that's the proven lower bound. So if anybody is trying to sell you a sort that has faster than n log n runtime, I don't know. Either they've discovered something the rest of the world doesn't know, or they're liars. So keep an eye out for that one. But do keep in mind, right, we've only talked about comparison sorts. We have not talked about niche sorts. Comparison sorts are these algorithms that can be applied universally to different types of things. Niche sorts are that idea that there do exist some algorithms out there to specifically sort specific types of objects. Okay, cool. Oh yeah, radix sort, actually, that's probably a good one to look into. That's another really popular one. You can look at some of those. Okay. Now we are going to talk about another algorithmic topic called dynamic programming. I know I'm not going to finish this today, so we're going to stretch this a little bit into Wednesday's conversation, which is fine, because Wednesday and Thursday, we are specifically going to be talking about one of the biggest unsolved mysteries in computer science. And dynamic programming actually kind of takes us in that direction. So what is dynamic programming? Dynamic programming is literally just a fancy term for an algorithmic optimization technique. So what I am talking about when I say dynamic programming is you are going to have some type of thing you are trying to solve with an algorithm. And if you can identify your final solution as a summation of smaller sub-problems that can be solved in the increasing order that you need them to, and you can store the answers to those sub-problems along the way, then you can ultimately sort of save up all that work as you're computing to get to the more complicated final solution. This probably makes no sense, but I'm going to give you a bunch of examples, and you can go out onto the internet and watch as many things as you want on dynamic programming, and I can guarantee you, I have been trying really hard to find quality content on dynamic programming, and it's not great. So if you find good stuff out there, please share it on the Ed message board. And pretty much the way that everybody has decided that this will be taught is, one, to tell you this is complicated. People get really intimidated by dynamic programming, and it feels really confusing. You are not alone. And 2, we learn it by example. So I'm just going to run you through a bunch of examples and hope that you'll eventually see the patterns that I'm talking about. So what is the thing that we're trying to do? So 1, dynamic programming can be applied when you have a problem that is at the start something that you can, quote, brute force solve with some type of recursive solution. And that makes sense, right? If I was talking about the definition of dynamic programming as you get the solution to the bigger problem by building up the smaller solutions, it's technically just an extension of divide and conquer. And divide and conquer is inherently a recursive kind of model, right? Like, how do I take my problem at the start and break it into a smaller problem and break it down and break it down and break it down until I get to a base case? We're kind of following the same general ideas here. But what's different about dynamic programming is we are going to break it down. So we start first with the recursive solution, like whatever that brute force is, and then we're going to go in and we're going to try and identify the overlapping subproblems. So how is this problem representative of a bunch of smaller problems put together? And then what we're going to do is the second general approach is what we would call memoize, not memorize, memoize. And what that means is that we are going to store the solutions to those subproblems as we go along and then reference them. So we sort of compute these subproblems, store them in some way, and then we can access them later. So that's like the first big transitional step. And then if you can, and I'm going to show you an example of this, you can take it another level further where you don't even have to like pre-compute all the subproblems. If you pick the specific order where you just build up the subproblems in a certain order, usually called the bottom up. That's sort of like where you compute the smallest kernel of the problem and then you compute up to the level of the problem you're looking for. Let's talk about an example. I think it gets a lot clearer with examples, like I mentioned. Okay, so let's go to a problem that I'm hoping that we're somewhat familiar with, this idea of calculating the Fibonacci sequence. Maybe this is one of the first examples you were given when you were learning what recursion is. It's sort of canonical in that way. So how can we solve this problem in the most optimized way? That's the question du jour. So also these slides come from my 492J class, which are sort of organized in the way you're supposed to respond to this in an interview question. So I always have this clarify slide to, if anybody in an interview ever gives you a problem, never start coding that problem until you ask them a bunch of clarifying questions. It's a secret requirement and they will judge you if you just start coding after they ask you the question. Is that bullshit? Yes. Why do they have secret requirements? Because gatekeeping, but now it's been said aloud, okay? So clarify, like can n be a positive number? Depends. N can be 0, but not negative. There's no such thing as Fibonacci's of negative sequences. Can we use additional data structures? In this case, yeah, we just want to get to the fastest. We don't care about memory usage. And then what's the result when n equals 0? Just to remind you, the sequence of Fibonacci is 1, 1, 2, I believe. So the result should be 0 before the first one, blah, blah. There we go. Here, also, this is the second level that I tell people to do in interviews. So 1, you ask clarifying questions. 2, you write down a bunch of examples because you clarify it. And let's be real, we engineers, we great at many a thing. Interpersonal communication might not be one of the skills for which we are renowned, okay? So when in doubt, clarify yet again. Ask your interviewer, hey, if I pass in this output, is this the output that this question is supposed to produce? Also, pro move, make your example clarifications your plan for your test cases at the end. Aha, then you've already agreed upon them. So here, for example, if we pass in n of 0, apparently there is no Fibonacci, the output's 0. So we pass in n of 2, the Fibonacci sequence is 1, 1, the output is 1. That's the Fibonacci of 2. 0, 0, so on and so forth. So you can see here, n, the overall Fibonacci is 34, but the sequence of Fibonacci to n is 1, 1, 2, 3, 5, 8, blah, 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 because just to remind you that the way that you calculate a Fibonacci number is adding the 2 previous Fibonacci numbers together. So 9, which is 34, is 13 plus 21, which is the Fibonacci of 8 and the Fibonacci of 7 added together. Does anybody have any questions about this problem, the Fibonacci sequence? Do you understand what we're being asked to do? I'm sorry I'm making a little assumptions that you're familiar with Fibonacci sequences. Yes?
Can you clarify the middle case 2 over time? So what happens? So what is 9?
So 9, the Fibonacci of any given value is the sum of the previous 2 Fibonacci values. So the Fibonacci value for 9 is Fibonacci 8 plus Fibonacci 7. So if I look at this sequence here, this is Fibonacci 9, this is Fibonacci 8, this is Fibonacci 7. And so we get the 34 from adding the 21 and the 13 together. The thing that'll mess you up, right, is that 21 is technically the summation of adding the 13 and the 8 together. The 13 is the summation of adding the 5 and the 8 together. The 8 is the summation of adding the 3 and the 5 together. The 5 is the summation of the 2 and the 3. The 3 is the 1 and the 2.
So the n refers to like the number in this, like the spot in the sequence.
Yes, thank you. Yes, that's a good clarification. So yeah, so when I say n, you're going to pass in a specific value, and I want the Fibonacci for that singular value. In this case, 9 would be the value 34, and we got there by going through this sequence. So the initial approach to this, which you may be familiar with, we taught a lot, is the recursive function. And so what you do is you just start with n and descending down recursively return the addition of the last and second to last numbers. And then we have a base case of when n equals 1. I'm going to show you what this code looks like on the end slide. Here we go. So this might be like the code that you are somewhat familiar with. Here we go. We take in n. If n is equal to or less than 1, you just return it because that Fibonacci is 1. The Fibonacci of 1 is 1. The Fibonacci of 0 is 0. That's what's happening here. Otherwise, you calculate Fibonacci by the sum of the 2 previous ones. So we're just going to let the recursion calculate that out for us, right? So when we get down to the very bottom, 1 will be returned up and summed and so on and so forth. This totally works. However, this is the call stack visualization of this code. So for example, if I originally passed 5 in here, I'm going to trigger 2 recursive calls. That's these 2 branches. So a Fibonacci of 5 is going to return Fibonacci of n minus 1, which is 4, plus Fibonacci of n minus 2, which is 3. And each of those is going to incur 2 recursive calls and so on and so forth. And so we end up with this exponentially expanding tree of recursive calls. Do we know what the overall big O runtime of this is? Yeah.
I think it was posted on the slide earlier.
It was, yeah. Do anybody remember what it was?
2n.
Yes, 2 to the n, 2 to the n, which is exponential and a really gross runtime. And if you look at this, hopefully your efficiency spidey senses are going off because, wow, how wasteful. I'm calculating the Fibonacci of 3 here and here. I'm calculating the Fibonacci of 2 here and here and here. And look at how many times I have to calculate the Fibonacci of 1s and 0s. Those are all separate method calls that I've got to create. Wouldn't it be nice if instead I used this magical thing called dynamic programming, that instead of just recomputing this whole thing from the bottom up, I saved the results of each of these calls and reused them later, so I don't have to recompute them. So here is our first memoized dynamic. Oh, look, it even auto-corrected. Why would you do this to me? Whoops, wrong one. Memoized. There we go. Here's our first memoized dynamic programming solution. So here what we do is, and this is a pretty common pattern in dynamic programming, the first thing we do is we need to take in a data structure that can store this work as we go along. So we are going to incur a little bit more storage space, but we're going to use that to save ourselves triggering more method calls. So here we can see that we have like a memo array, and what we can do is initially make sure that array is full of nulls. And then we can see, hey, we will fill up this array as we find the answers to things. And so right away, we can check, is this value of n already evaluated in our array? If so, just return it. Don't even get into this base case or this recursive case, which is going to just sort of like nip those recursive calls right in the bud there. And then otherwise, you can see this looks exactly like the base case of a recursive solution for Fibonacci. And then here, this also looks just like the recursive case of Fibonacci. Look, this looks exactly the same, except instead of just returning Fibonacci of n minus 1 plus Fibonacci of n minus 2, I calculated those things as a result. I stored the result in the memo, and then I returned it. So this is exactly the same code as the previous slide, except I've added this extra array that's going to be filled up, and I use it to prevent myself from recursing. So here's that same call tree from the previous slide, but now it will calculate each of these on its first sort of pass. But now when it comes back around and tries to run Fibonacci of 1, that space in the memo array will be not null. So it'll hit this like super base case and immediately bail out. And so you can see, look at how many of those recursive calls we are just going to essentially handle with an immediate return. And so then our runtime for this is not going to be sprouting all of those branches of the recursive calls. Instead, we're actually going to end up with only 2 plus 1 calls that result in an actual recursive call, meaning like we enter the actual recursive case down here, which means we just took this from a 2 to the n runtime to an n runtime, which is dramatique. I don't know how to tell you how dramatic that is, but that is like, can we do any better when it comes to algorithm optimization? And literally all we did was just remember the work we had already computed as we went along. Yeah.
I was taking a look at this. Does this consider the head case of when we pass the number 0?
I believe it may or may not just need an less than. Maybe this base case just doesn't have the less than here. Yeah. Yes, but thank you. Yeah.
Really quick, why did it change from like 0 and 1 to 1 and 2 for like n for the base case parameter?
Oh, sorry. This is just, yeah, and to your point too, this is, there's actually a few different sort of definitions of Fibonacci, and it's just whether or not you carry it down to the 0th case or not, and that's what happened here. I pulled these from 2 different sort of definitions. Same sort of general idea. Yes?
So how do we, so say that we are on Fibonacci, like the 9th Fibonacci number and it's in our like memo,
Mm-hmm.
will that be stored in like the 9th index or?
Yeah. So what's interesting, right, is like if I call Fibonacci of 9, right away, that's like I'm going to start with an empty memo. But what it is going to help me do is it's going to help me from not having to repeat anything within that singular call. And what's going to eventually happen is you can see we store things at the memo of itself, like memo of n. So when we get down to our base case down here, if n equals 1 and n equals 2, we just return 1. Really, for anything that is n of 3 and greater, we're going to fill up that result. And so memo of 3 will store the 1 and the 1 added together, which will be 2, because the Fibonacci of 3 is 2, and then so on and so forth. So we're going to store the solution for the given n at the index, that index in memo, which is really convenient because these values are ints and the indices of the array is also an int. So it makes this nice and convenient for us. Yeah.
I have a separate question, but
Sure.
are these slides posted yet?
These ones probably aren't posted yet. I just made these. So yeah, I will get these posted, I promise. Yeah, question.
So why again do you not pass the array memo to the next calls of fib?
Oh, you're right. Sorry. This probably does need like the comma memo right here. That's what you're saying. Yes. I will fix this pseudocode. Good job, y'all. Yes. Can we take it a step further? I mentioned that, okay, like this is helpful. We're kind of going from 9 down, right? And we've eliminated all of these method calls, but I mentioned there was that third step to dynamic programming. So this is really convenient because we know just by the nature of Fibonacci, starting from the top and going the way down, we've got to compute the previous subproblems. That's just literally baked into the definition of Fibonacci, which is why we can't stop using this example to talk about recursion. Somebody sometime please tell me that Fibonacci is actually used for beautiful things out in the world. I don't know what it's used for. But what if instead of going from the top down, we went from the bottom up? So here now is a totally non-recursive Fibonacci solution where what we do is we take in the n, we make a new array of n plus 1, we fill in the spaces in the array. We automatically know this is essentially our base case right here, right? And instead of going from the top down, we're going to go from the bottom up, which is going to save us even more time because we don't even need to like let recursion take us down to the base case. We're just going to start at the base case. We're going to fill up this array and we're just going to loop until we get to n. And then we know by the time we get to n, rad, we can just return that thing. And we're just going to fill up the array and then use the things we just added into the array to fill up the later parts of the array. So even fewer recursive calls. Huzzah! We've got it even more efficient. Any questions on the bottoms up approach?
Okay. Would this be still O of n or?
This is still going to be technically O of n runtime because as you can see, right, like I'm going to loop from what is essentially the bottom of the stack up to n. So asymptotically, this is the same as the previous one, but I'm going to have better sort of constant factors because I don't have to go in and like open up a new method just to hit this base case and then bail out. Yes?
What if we did both? Like remembered a list in the thing forward and then counted up forward?
Remembered, so like, whoopsies.
So like you have like a map or like an array where you have like everything from before, like a global array.
Oh, you mean like between multiple calls of Fibonacci? Yeah, so for example, like let's say you have a Fibonacci object that's going to persist across multiple calls to Fibonacci, definitely. And I think that is a natural extension of the thought process behind dynamic programming. And again, to kind of draw another line for you, right? Like dynamic programming is technically optimizing a later call by storing information it previously did, a lot like how path compression kind of makes your structure a little bit more efficient for later calls to find set. These are all algorithm optimization techniques and a few different sort of examples. I don't think I have full time to really walk through this last bit, but if you go in here, there's actually a fourth level even freaking deeper than just counting from the bottom up, because technically, do we really care about storing all of the Fibonaccis from 1 all the way up? No, we only really need the Fibonaccis of the latest 2 before the one I care about. So why am I building up this array and storing all of them as I go along? Instead, what you can is you can just create 3 variables. One that holds on to the second to last value, one that holds on to the last value, and one that holds on to the current value. And just kind of rotate those pieces of information in and out of those places so that I am in further reducing my memory usage. So this now has officially taken me from 2 to the n with a massive memory usage because of all of those method calls, all the way down to not even using a full array. I'm only using 3 variables. And here you can see the actual code for that. It looks very, very similar to that array implementation that we had, but you can see here I just have 3 variables, A, B, and C, and I just start A and B at, you know, the base cases for Fibonacci's, and then I just sort of rotate the values in and out and return B, so I don't even need the array. Clever, right? I will say this particular implementation of Fibonacci, I have literally never seen in an interview, and people still ask Fibonacci in interviews. It was literally my tech screen question when I was a dev at Microsoft. Isn't that hilarious? Kind of embarrassing for them. But yeah, you can actually clock these things on LeetCode. In this particular solution,
literally runs, and it's crazy. It says it runs 100% faster than all the other solutions of Fibonacci on LeetCode. So this is, as far as we are aware, the fastest solution to Fibonacci out there. And the best on space, too, which is also what kind of contributes. You don't have to purchase in space. Thanks so much, everybody. We'll probably do like one more dynamic programming example on Wednesday, but come back for the mystery that is P versus NP. We'll talk about it. Thanks so much, everyone.